Hello, everybody. So my name is Mario. I'm from Grafana, and this talk is about the journey from the lower layers of our users' systems to the upper layers of a cloud provider, and how do we extract data and how can we use it for monitoring network at different layers and eventually slashing some or reducing some costs associated to it. This story started with when some of our users were reporting that the data transfers between availability zones in their cloud accounted for roughly 25% of their public cloud users. You know, some cloud providers have different availability zones. The traffic within the same availability zone is for free, but when you cross the borders of that availability zone, you might have to pay an extra amount. This is we are Grafana. We are a company that provides dashboardings, but also provides data storages for storing metrics, traces, and we overall work in the observability system. We need to inject, if you want to observe your network or your applications, you need to inject into your systems probes or monitoring agents that will extract that data. And here is where eBPF comes. I'm not sure if everybody who has heard about eBPF previously. Okay, just few of you. eBPF is a technology that is shipped inside the Linux kernel since some years ago. This technology allows you to inject programs, pre-compiled programs, in different layers of your operating system and applications. This is a very basic layer architecture. Imagine you have your Linux kernel with your operating system runtime, with some syscalls and applications running on top of it. eBPF provides a set of toolings. One is a verifier and a just-in-time compiler that allows you to injecting small programs at different layers. That means in the network, in your network's stack, in your operating system runtimes and syscalls, and even it allows you injecting programs into the running applications without having to recompile them nor redeploy them. Is automatic. This allows you either modify the behavior of your system, of your network stack, your operating system runtimes, and even your applications, but it can be also used for observability. So your eBPF-based solution is a regular application that has some special privileges to connect to this eBPF infrastructure into your kernel in order to inject programs and communicate with them, exchange data with them in order to monitor or observe what's going on. The advantages is, like, as I said before, you don't need to rebuild your applications if you want to instrument them with eBPF. You don't need to redeploy your system. You get native performance because eBPF has a just-in-time compiler that will execute your programs, and it provides safety. This eBPF just-in-time compiler pre-verifies your program in order to make sure it doesn't do any dangerous thing. I mean, by dangerous things, I mean, for example, dangling pointers. eBPF is not magic. sometimes it has become a buzzword in some fields like observability and security, and sometimes it's treated as magic, but no, they are just binary programs, and whatever you want to instrument, you need to know how it's organized at a binary level and how it works at a binary level. Grafana Bela is the approach for automatic instrumentation and network monitoring provided by Grafana. That means you install into your Linux kernel or into your Linux system, you install Bela, and you can get automatically network metrics, application level metrics, and even traces. Just to set a common mindset, by a metric, I mean the status of some part of your system at a given point. For example, how many bytes are being transferred between two given endpoints at a given time. By traces, I mean an event that has a start, has an end, and has a series of attributes. For example, a file transfer. It starts, it ends, and it might have some extra attributes that could be reported as a trace. So Bela will send data, can export the metrics and traces via OpenTelemetry. Do you know, somebody knows what is OpenTelemetry? Okay, few of you. OpenTelemetry is a standard and open format for exporting your observability data, metrics, traces, logs. This is not a single company protocol. This is a protocol where most of the big observability companies and small observability companies are investing, because this allows removing your vendor lock-in. Once you have your solution exporting your data in OpenTelemetry, you might switch your observability provider. So via OpenTelemetry, Grafana is able to export to different data storages. For example, we provide Tempo to store in traces and Mimir to store metrics. They are open source solutions, but you might use other data storage like Prometheus, Jagger, and so on. And this data is then visualized in Grafana, which is a part of a company, is a product itself for visualizing dashboards. So how eBPF allows instrumenting your network? The network can be automatically instrumented at different layers. As we said before, eBPF provides different kind of programs that can be injected in different parts of your system to instrument how network and applications are instrumented. This is a raw example. With eBPF, you can inject traffic control or express data path programs into the Linux network stack, and it will provide you information about your network packets, which interfaces they go through, which hardware addresses, which IP addresses, ports, and so on. And you can go up into the layer you can go to kprobes, which are programs that are injected in the kernel in order to know the status of your connections. And you can inject user probes in the libraries and the executables to get more information about the application, like which protocols are being used, your method calls, what the different services return for a given call, etc. This is, as we say, this is not a unified magic solution. This is depending on what you want to instrument. So you need to inject different sets of programs depending, for example, which language is your application written in different runtimes, are implemented in different ways. So you will need to instrument them in different. So we have all the puzzle pieces. We need to get them or to you need to join them. So you need to join them at the a network. An eBPF program basically just is triggered every time a given event is done. For example, you inject it into your network stack and you will get visibility of all your packets. In order to compose metrics from it, you need to store all this information in tables, for example, in maps, with all the source and destinations of your packets and your connections, and then account them periodically in order to build your metrics. There is a metric named Baila Network Flow Bytes, for example, that will show how many data goes from one endpoint in your system to another endpoint. It might be in your system or an external. You just get a count of the packet data, and you can provide a network, for example, from a given source IP and port to a given destination IP and port. You get a number of bytes, for example, 1357 bytes. A metric usually is a name for the metric, a set of attributes, in that case, source and destination, and the value for that metric. We can get metrics at different levels. For example, L3, L4, this will be an L3, L4 network metrics, basically captures bytes or packets. And they have an advantage that they are robust metrics because they are based on stable APIs and standard binary representations. The TCP/IP network has been at the binary level stable for decades. It doesn't change, so you just need to parse that. The problem they have is that they just provide very basic information about your application or about your system. Source and destination endpoints, packet counts, byte sum. It can provide some extra attributes like Ethernet protocols, interface names, and so on, but it provides information about your connection, but doesn't really provide information about your applications or your systems. Apart of that, this data needs to be enriched for many people. I observed the profile of many people attending here that maybe is fine with this. No? What eBPF sees, we see the source address, source port, we see some numbers there. Even for a network administrator, that could be too high level. It would prefer even hardware level data, which is possible to get it also with eBPF. But what most of our users require, they don't really want to know this. They want to get something more human readable. For example, the source and destination services. This is an example of what Kubernetes users need. Kubernetes is another word. Can raise the hand who knows what is Kubernetes? Barely knows. Okay, basically Kubernetes is for application and services development and deployment. Is a system that allows you grouping, defining your applications and deploying it in distributed systems. Kubernetes facilitates virtualizing and packing your application as containers, and it also provides mostly software-defined constructs to manage and configure the applications. For example, it also provides software-defined networking. In Kubernetes, even if internally it works as IP addresses, it associates the network data with those Kubernetes constructs, like, for example, owners might be deployments with replica sets, can group applications in namespaces, and so on. So this is what our users need. But eBPF works at a very low level, and Kubernetes constructs are at a high level. So that's where Kubernetes informers come to the rescue. Kubernetes has its own API. It's a HTTP API in which you can interact with it in order to deploy new applications, get their status, and so on. But it also allows to interacting with the API to get a snapshot of all your running applications, services, processes, and so on. It gets the information, so we maintain in always a database that maps every IP in our system. A map between this IP in our system to the resource it belongs to, because even if you run Kubernetes in 2-3 physical nodes, every application you run in Kubernetes or every container, every pod has its own IP. Kubernetes will define IPs for any independent application or service in your system. So we need to keep track of them in order to know what IP belongs to what service. It might happen also that your Kubernetes application or service is communicating, is interacting with an application that is outside of your system. For example, it performs a request to an external service. This information of that external service is not available inside Kubernetes. Kubernetes maintains its own internal DNS, and that's why we get via informers, but we might not have the DNS information of an external service that we want to map a name with an IP. We might rely on an external reverse DNS, but sometimes this might be expensive. However, we can make use also of eBPF to build our own reverse DNS. How do we build our own reverse DNS? If our DNS program, eBPF program, is triggered on every packet in our network stack, we might listen for DNS packets and inspect what's inside of that DNS packet. So every time an application in our system tries to connect to an external application and does a DNS request, we can build the map of IPs and host names that might be used also to identify not only the internal traffic, but the external traffic. Kubernetes maintains information about the physical nodes, not only about a pod. For example, a pod is an instance of a process of an application, but we can also get information about the nodes, the physical nodes, what you buy to your cloud provider, this virtual machine you buy to your cloud provider. And a very useful information you can get for that is some labels describing some metadata about it. And one of them is the availability zone of that node. You can, for a given IP address, or a pod IP address, you might know this pod, which is a process that can be sending information to another pod. Do you know which node this pod belongs? So you can merge that information with your node information, and you will know also in which availability zone. So Bela can provide in the network metrics can provide also the source zone and destination zone of your traffic. That will allow you identify how much traffic goes from one availability zone to another. There are many attributes to choose from, not only zone and IP and port. There are many, this is part of our documentation, but you need to choose what is important. So there is a thing named cardinality in most metrics databases. That means that the more combination of attributes you store into your database will exponentially increase the size of your database and the cost of your database. So it's important, for example, to select which attributes are important to you. In this example, this is an example configuration of Bela in which for each metric you can select which attributes are important. For example, the source and destination owner names and the source and destination zones. This will be a configuration for someone that don't really care about IP addresses nor MAC addresses. Then this information can be visualized. When you have this metric showing you source, destination zones, and names, you can use, for example, Grafana to build your service graph, and you will see all your pods, all your services, how are communicated. And you can use query languages to visualize your data. For example, this is a real use case from a development cluster internal to our. We wanted to know how much traffic we were spending or how much money we were spending in inter-availability zones. So this metric is stored, this Bela network metric is stored in our Mimir data storage, and you can use PromptQL. PromptQL is an open query language that is not created by Grafana, is created by the Prometheus by the Prometheus organization, which is an open source time metrics database, to summarize the number of or the amount of traffic between availability zones. And we can see that this traffic is more or less low, but there are two in a given cluster, this dev US East cluster between two zones. You can see this traffic that represents at the open price. I mean the price is public. I don't for intertraffic. I don't remember exactly how much was it. Was like 10 cents or 1 cent per gigabyte, but that at the end, in one of our smaller development clusters, that represents 4 figures per year in terms of euros or dollar or pounds, which is a non-negligible expense. This is only a small one. Imagine in biggest clusters, which we already have, that might be an amount of important in your bill. So can this be reduced? We can filter not only traffic by source zone and destination zone, but which applications are spending most of that traffic. So in this query, in this new query, we say, okay, we want the top 3 pairs of owner name and destination owner name for that cluster and that destination zones. This has been anonymized for confidentiality reasons. Kafka. I don't know if you, it's, at the end it was, but basically this chart shown that 90% of our interzone traffic, or 80% of our interzone traffic, was spent in the replication of a message queue protocol. So addressing that will allow us reducing the traffic. So we are now investigating whether it's worth, for example, instead of sending the data between those instances, it's better doing it in raw data or doing it compressed, paying an extra amount of CPU at the advantage of reducing the network traffic. This is Grafana Bela. This is an open source project from Grafana. It's open source. Anyone can collaborate. But we recently donated it to the OpenTelemetry Foundation. As I mentioned before, OpenTelemetry is an open foundation formed by multiple partners in the observability field. We donated Bela to it under this name, OpenTelemetry eBPF instrumentation. That doesn't mean that Bela is going to stop business or being deprecated. We will also maintain it, but using this OpenTelemetry eBPF instrumentation project as an upstream. So if you are more interested on it and you want to collaborate or to know the community, you can reach us, one, in the Grafana Bela GitHub. You can see there the Bela code, write there issues, any problem you have, or contact us in the Bela channel of our public Slack. If you prefer to go directly to the community, and to the open organization, you can also find us in our OpenTelemetry eBPF instrumentation GitHub, and also in the OTel eBPF instrumentation channel in the Cloud Native Foundation Slack.